The continuation of the previous lecture. Already we discussed the two problems in the previous lecture. Now we'll discuss the third question. So in this particular problem, we will perform the convolution integral problem in a graphical method. Here you can see the two signals are given, x of t and h of t. We need to find the signal system output, y of t, and we will do in a graphical way. U of t minus u of t minus 2 plus u of t minus 5. So it's actually a combination of three signals, the step signal. So we'll try each one. First, we will try what is U of t. U of t means unit step signal, which is equal to 1 for t greater than 0 and 0 for t less than 0. Means this is the graph for U of t, and here if t is greater than 0, the function magnitude is 1. So this is the signal U of t, okay, which is equal to 1. So here you can see the variable is t. Now we need the second signal, that is minus 2 u of t minus 2. So we'll try u of t minus 2 first. So u of t minus 2 means it's a shifted version of the step signal. Either you can directly draw or I will write the definition here. U of t minus 2 means which is equal to 1 for t minus 2 greater than 0, or you can write t greater than 2, and 0 for t less than 0, or sorry, t minus 2 less than 0, or you can write t less than 2. So if you observe this particular graph, here you can see that signal starts from 2 onwards, and if t is greater than 2 means towards right. And one more thing, here the amplitude is 2. So if you consider the signal 2 u of t, so if it is 2 u of t, you need to write 2. So the amplitude of the signal is 2 here. So you can draw a signal like this with the amplitude 2. So this is a signal 2 u of t minus 2. So signal starts from 2 and the amplitude is 2. Now we need to draw u of t minus 5. It's simply a shifted version of the step signal, which is equal to 1 for t minus 5 greater than 0 or t greater than 5, and 0 for t minus 5 less than 0, or you can write t less than 5. So this is a point, and here the magnitude is 1. So from 5 onwards, the signal amplitude is 1. That's mean. Okay. Now we need to perform the operation u of t minus 2 u of t minus 2 plus u of t minus. So we need to add different signals. Then you will get x of t. So if you observe the first signal, the non-zero magnitude starts from 0 onwards. So from this particular point and up to 0, that is from minus infinity to 0, the first signal magnitude is 0, second signal is also 0, and third signal is also 0. And if you perform u of t minus first signal minus second plus third, you will get 0, because there is no signal amplitude. So all the signals having 0 amplitude. Next, we can observe that from 0 to 2. Okay, from 0 to 2, the first signal amplitude is 1, and second signal amplitude is 0, and the third signal amplitude is 0 for this particular limit, 0 to 2. So you'll get 1 minus 0 plus 0. So you'll get 1 here. From 0 to 2, you'll get 1. Okay, and from 2 to 5, if you observe the signal 2 to 5, the first signal amplitude is 1, second signal amplitude is 2. So if you perform the first signal minus second, means you will get 1 minus 2, that is minus 1, and the third signal amplitude is 0, okay, for this particular limit. So 1 minus 2 plus 0, you will get minus 1. So we can draw a signal with amplitude minus 1 from 2 to 5. So here the amplitude is minus 1 up to 5. If you observe the signal from 5 onwards, the first signal amplitude is 1, second signal amplitude is 2, and the third signal amplitude is 1. So 1 minus 2, because u of t minus the second signal. So 1 minus 2, you will get minus 1, and the last signal is plus u of. So you need to add the last amplitude, that is plus 1. So you'll get 0. From 5 onwards, the signal amplitude is 0. So this is the signal x of t. From 0 to 2, 1. From 2 to 5, it's minus 1. And similarly, we need to draw the signal h of t, which is given by e raised to 2t into u of 1 minus t. So e raised to 2t means as a signal, it's an exponentially growing signal. And if you observe the signal at t is equal to minus infinity, if you observe the t is equal to minus infinity, the equation becomes e raised to minus infinity, which is tending to 0. And at t is equal to 0, you will get e raised to 0, which is equal to 1. And t is equal to infinity, it's e raised to infinity, which is equal to infinity. So it's an exponentially growing signal. So the signal passes through the point 1 and it's going to infinity. This is the signal e raised to 2t. Now we need to multiply the given signal with u of 1 minus t, and u of 1 minus t means 1. It's a shifted version of the step signal, and it's also time reversed. So here you can write this condition is valid for 1 minus t greater than 0, or you can write minus t greater than minus 1. If you multiply with minus 1, you need to change sign, so it becomes t less than 1. And 0 for 1 minus t less than 0, or minus t less than minus 1, or t greater than 1. For t greater than 1, the function magnitude is 0. From this point onwards, signal amplitude is 0. And if t is less than 1, the signal amplitude is 1. And if you multiply these two signal, okay, you will get a signal which exists only in from minus infinity to 1. Okay, you will get something like this. Okay, a signal which is exists only up to 1 from minus infinity, because we will multiply this exponential signal with the step signal, and which passes through the point 1, and it's going to 0 when t tending to minus infinity. So this is a signal e raised to 2t into u of 1 minus t. Now we got the signal x of t and h of t. Now we can perform the convolution operation. So this is the convolution operation, x of t convolution h of t, which is given by integral minus infinity to infinity, x of tau into h of t minus tau. So if you observe this particular equation, we required x of tau and h of t minus tau. Now we have x of t and h of t. From this, you can find out x of tau and h of t minus tau. So we'll see how we can find. So if you know x of t, simply you can find out x of tau by simply replacing the variable. So here you can see the variable is t. Now we can change the variable to tau. So you'll get exactly the same waveform by simply changing t to tau. So you can see x of t and x of tau shape similar, but the variable is here tau. Similarly, if you know h of t, simply you can find h of tau by simply replacing t with tau. So now we can see the variable is tau. But in order to plot h of t minus tau, first we will draw h of t. From h of t we will draw h of tau. From h of tau we will draw h of minus tau. From h of minus tau we will plot h of minus t plus minus tau plus t. So it's simply h of t minus tau. Okay, so we already got h of tau. Now we need h of minus tau. H of minus tau means simply the time reversed version of the signal. So here the signal starts from 1 onwards. So if you perform the time reversal, uh, you will get a signal which is a mirror image of the signal h of tau. Okay, so signal start from minus 1 onwards. And here you can see the signal starts from minus 1 onwards and it's going to infinity. And this is h of minus tau. Now we need to find h of minus tau plus t. So h of minus tau is here. Now we need to find plus t. So we can add plus t here. So we'll get minus 1 plus t. So your starting point becomes minus 1 plus t, or if you rewrite this, you can see the t minus 1. Either you can plot the signal towards left side or right side, because we don't know the value of t, because it's here the variable is tau. So we don't know the value of t. So I can draw a graph either towards left side or towards right side. Okay. Uh, Assume that initially I will plot the signal like this, and assume that t minus 1 is here. Okay, this is the signal h of t minus 2. Now we need to evaluate the integral for different values of t, because we don't know the value of t, so we'll take different cases of t and we will find y of t. And first assume that we are plotting the signal and x of tau starting from 0 onwards, and assume that your signal h of t minus 2, it's somewhere here. Okay, and this is the case where the starting point of the signal is t minus 1. This is the signal h of t minus 2. So assume that this t minus 1 is less than 0, because 0 is here and this is t minus 1. And t minus 1 is less than 0, or you can write a t less than 1. And for this particular interval, we need to find, or we need to evaluate the integral equation y of t. See, it's actually start from minus infinity to infinity. But if you observe this particular waveform, your h of t minus tau starts from t minus onwards, but x of tau is having non-zero magnitude only from 0 onwards. So you can start your integration from 0 onwards. 0 to 2, you can see the signal amplitude x of tau, it's 1, and the h of t minus tau, you can see that some overlapping is here. Okay, if you observe these two signal here, h of t minus tau amplitude, you can draw it's simply e raised to 2 into t minus tau, because already we studied h of t is e raised to 2t into u of 1 minus t, and for this particular duration from t minus 1 to infinity, or you already identified that u of 1 minus t is 1 for a particular limit. So if you simply substitute t to t minus tau, because we required h of t minus tau, if you substitute t minus tau here, it is e raised to 2 t minus tau. And if you substitute in this particular equation, it's simply u of 1 minus t minus tau. Okay, and this step signal amplitude is 1 in this duration, so only we'll consider the amplitude e raised to 2 into t minus tau. Okay, now we'll substitute here and remaining value is 1 d tau, plus you can see that from 2 to 5, the x of tau amplitude is minus 1, so x of tau is minus 1 into, again h of t minus tau will be the same signal, so you can multiply e raised to t minus tau d tau. Okay, so this is the integration equation. Now we can integrate this. So here remember one thing, tau is the variable, so you can consider t as a constant. So if you integrate here, the term e raised to 2 t minus tau, and you'll get a minus 2 as a constant in differentiation. So minus 2 will be the denominator, and now we need to apply the limit 0 to 2. And the second case, again, it's not plus, actually, it's minus e raised to 2 t minus tau divided by minus 2, and the limit is from 2 to 5. Okay, now we need to simplify this relation. So if you simplify, you will get okay, like minus 1 by 2 is outside. For both case, there is 1 by minus 2, so you can take outside. So remaining, if you consider it's e raised to 2, now we are substituting for tau. Okay, because tau is a variable, so we'll substitute this limit for tau. So it's t minus 2 minus e raised to 0. Okay, and for the second case, we are taking so already there is a minus e raised to 2 into t minus 5 minus e raised to 2 t minus 2. Okay, now we can simplify this equation, so it becomes minus 1 by 2 into If you observe this, there is a term e raised to 2t minus 2 and e raised to 2t minus 2. And if you apply this minus, it's become plus. So you'll get 2 e raised to 2 t minus 2 uh, minus, sorry, actually here it's a small mistake. I'll correct it, because if you substitute the limit here, actually we'll apply 0 here, so you'll get e raised to 2 t minus 0. Okay, that's a term. So you'll get e raised to 2t. Okay, now if you open the bracket, it becomes e raised to 2t minus 5. Okay, this term is already added with the first term. So this expression, if you multiply with the minus, equation order will change. That's all. I think the first part is okay. Now we'll move to the second equation. Now if you consider the second equation, now already consider t minus 1 less than 0. Now we can consider t minus 1 is greater than 0, but it is less than 2. Now we can consider a case t minus 1 is greater than 0, but it's less than 2. Or if you rewrite this, you will get, if you consider the first two cases, you will get 0 less than t minus 1. So you can write 1 uh, or t greater than 1. And if you consider the last two cases, t minus 1 less than 2, you can write minus 1 becomes plus, and 2 plus 1, that is 3. That is t is between 1 and 3. And you can write the equation y of t here. Now we can say this is t minus 1, which is greater than 0 and less than 2. So we'll consider one case. And if you consider the overlapping area here, the first, you can start from t minus 1 onwards and up to 2. Here, x of tau is 1 and h of t minus tau, we know that it's e raised to, this is h of t minus tau. It's simply e raised to 2t minus tau, because we already written that d tau. Plus, for the second part, from 2 to 5, again, it's 2 to 5. Again, you will get e raised to, sorry, minus 1 into e raised to 2 t minus tau d tau. Okay. The second part is we already evaluated. Again, the same equation, 2 to 5 minus 1 into e raised to 2 t minus 2 d tau. So you can write exactly the same thing. For the first part, you can write it's minus 1 by 2. On integration, you will get, and the term e raised to 2 t minus tau, and the limit is from t minus 1 to 2. Okay. And if you consider this, second term is minus e raised to 2 t minus 2. Okay, already we taken this minus 1 by 2 outside. Okay, so the remaining term is 2 to 5, because we return minus 1 by 2 as a common term, because we know the for the second term also there will be minus 1 by 2. Okay, on integration. And if you simplify this, you can write it's minus 1 by 2. The term will be e raised to 2 t minus 2 minus e raised to 2 t minus, in place of tau you can substitute t minus 1. So you will get t and plus 1, because minus 2 actually. So in place of tau, if you substitute t minus 1, it becomes minus t and plus 1. Okay. Now we can simplify the remaining portion. So if you consider this, it becomes 2, because t minus t is 0. This is the first term. And the second term, you can see that it's already written. It's e raised to 2 into t minus 5 minus e raised to 2 t minus 2. Now if you consider these two terms, there will be term minus 1 by 2, and for the second term again it is 2 e raised to t minus 2, because the first term and the last term is same, so you can add these two terms, and second term is e raised to 2, and the last term e raised to 2t minus 5. Okay, so this is the next case, and now we can consider third case. Now assume that the t minus 2 is greater than, this is t minus 1, which is greater than, or h of t minus 2 lies here. So if you observe here, there is only one integration we require, that is you can write t minus 1 as greater than uh, sorry it's greater than 2 and less than 5. So between the limit 2 to 5, t minus 1 lies between this limit, or you can write t minus 1 if you consider the first two cases, and if you rearrange you will get it's greater than 3, and if you consider the last two cases t minus 1 and 5, you can see that it's less than 6. And for this particular limit y of t, you can write simply it's from t minus 1 to 5. Here the amplitude is minus 1 into e raised to 2 t minus 2 d tau. Okay, so if you take this minus 1 on integration, you will get again 1 minus 1 by 2, so it becomes plus 1 by 2, and the remaining e raised to 2 t minus 2, the limit is from t minus 1 to 5. And if you simplify this, you'll get 1 by 2 e raised to 2 t minus 5 minus e raised to 2 t minus, in place of tau you can substitute here, so tau plus 1. So on simplification you'll get 1 by 2 e raised to 2 t minus 5 minus, if you simplify these two you'll get e raised to 2. I think this is the third term. Now I can conclude the last case, that is t minus 1 is greater than 5. So this is actually h of t minus 2. Here y of t, that is t minus 1 is greater than 5, or you can write t greater than 6. In this particular limit there is no overlapping area, so y of t becomes 0. Okay, we got different cases, and so we can conclude the final result like this. Finally, you can conclude the answers. It's simply multiplied with the minus. That's why it's 1 by 2. Already we written in terms of minus 1 by 2. So there will be a small change in the final representation, because if you multiply with minus, the order will be changed. That's all. So this is the final result of the given signal. Okay. So this waveform is very difficult to plot the final result. So we'll simply write the final equation. Okay. Thank you.